Howdy, let's pick up where we left off in our electrochemistry topic, where today we're going to give an overview of electrolysis, investigating electrolysis and predicting products from the electrolysis of both molten and aqueous compounds. Previously in this electrochemistry unit, we've introduced some of the key concepts we're really going to apply and build on throughout this next part of the topic. Things like, oxidation, reduction, redox reactions, oxidizing, reducing agents, oxidation states. All really important ideas that allow us to build on these topics and start to apply them in what I think are much more interesting and applicable ways. So we're going to give a brief overview to begin with of what has been covered, but there's a couple of videos in the Electrochem series that do deep dives on all these states, so it might be worth consolidating there if you're not feeling too confident here when we begin to reintroduce these ideas. So importantly, we've got redox reactions. These are the keys for what we're going to be looking at in the electrochemistry topic from here on. A type of chemical reaction where it undergoes both reduction and oxidation simultaneously. So you've got one species that's undergoing reduction, one species that is undergoing oxidation. What is reduction and oxidation? It refers to the loss of electrons and it refers to the gain of electrons. This acronym OILRIC, really useful to help us remember this, that oxidation is loss of electrons, reduction is gain of electrons. In a redox reaction, there's a transfer of electrons. So we know we've got all our conservation laws. We've got the conservation of mass. We can't create or destroy matter. So in a redox reaction, the species that is being oxidized, the species that's losing its electrons are losing it to the species that is gaining them. Therefore, the species that is being reduced. We can look at the electron transfer or changes in oxidation numbers or oxidation states to determine if a redox reaction has occurred. And we can represent these as half equations to show these two processes, to show the loss of electrons and to show the gain of electrons. So these are where we actually have the electrons in the equation. So for example, we have the oxidation of a metal, magnesium, to form a cation where it loses electrons. So we have our magnesium atom forming a magnesium ion where we've lost those two electrons, thus an oxidation process. We could show the reduction of a non-metal. So we have an oxygen molecule that can gain electrons in order to form an oxide ion. Thus we've got a reduction reaction. We've gained the electrons here. As I just said before, there has to be conservation of mass. So if something's losing electrons, something else needs to gain those electrons. Those electrons have to go somewhere. So then we can write overall equations to show this whole redox process. Both atoms and charge need to be balanced in the half equations. So, as with any equations, they've got to be balanced. So we've got to balance the atoms, and then you've also got to balance the charges to make sure that they are all nice and conserved. Now, in order to combine our half equations, we've got to make sure that the electrons cancel out. So the same number of electrons that are lost in oxidation need to be the same number of electrons that are gained in the reduction. So for example, in this one that I have here, our magnesium atom is losing 2 electrons, but in order for the oxygen molecule to be reduced, it needs to gain 4 electrons. So we've got to balance the electrons in the half equations. So that means that this equation has to essentially happen twice for every one time that the oxygen reduction occurs. So we'll have to multiply this by 2. So 2, 2, and then 4. And then once our electrons cancel out, we can quite simply just combine what's on the left-hand side for the oxidation and reduction processes, what's on the right-hand side for the oxidation and reduction processes to show that total overall equation, which in this instance would be 2 magnesiums plus 1 oxygen goes to 2 magnesium ions plus 2 oxides. So we're showing that redox process, and we can confirm that we have a reduction reaction by checking the oxidation states, the oxidation numbers, which is a number that we give to an atom in a compound that describes how oxidized or reduced it is. And we have a whole bunch of rules for determining what the oxidation numbers are. So in this instance, we got elements just in there in their standard state there. So they're going to be neutral, 0, and then we've got ions here. So we're going to be +2 and -2. And we can observe how these oxidation states are changing. So we have the oxidation where the oxidation number is increasing. We have the reduction where the oxidation number is decreasing. Like I said, 2 other videos previous to this that you can go and recap these ideas in a lot more depth. But for now, we're going to start applying all of these in really useful and interesting ways, like I said earlier. Because if we're dealing with the transfer of electrons, what we're dealing with now is we're essentially dealing with electricity. You can think of electricity as a flow of charge, if you like. So we have electrical energy. So we have all these fantastic conversions that can take place. We have energy stored in chemistry and chemical bonds in atoms and molecules, and we can transfer that into electrical energy. And we can also do the vice versa, which leads me into the first main topic on our series, which is on electrolysis. So let's break down the word, as we often like to do. I think that's really helpful to help us understand what it means. I mean, it's got electro there, signifying electron, signifying electricity. And then lysis is a word you might be familiar with from a subject like biology, from Greek, meaning to split. So where we've got electricity, splitting with electricity, we can think of that as meaning. So in this instance, we have electric current being used to break down a substance that is made of ions. Essentially, we're using electricity to drive a chemical reaction. So a chemical reaction that might not take place of its own accord, we can use electrical energy and we can convert electrical energy into chemical energy. We can also do the opposite. We can take chemical energy, which is what we just saw, and we can transfer that into electrical energy when we have that flow of electrons. So these kinds of chemical reactions are what are occurring in batteries. I got a fancy little power bank here, and you can think of this power bank when I'm using it not plugged in. We got energy stored. It's chemical energy, and then if I've got to power something, what I can do is I can drive a redox reaction and convert chemical energy into electrical energy. But then what do you do at the end of the day when your power bank or your phone or your laptop, whatever your device you're using, is you plug it back in to recharge it. So here, I've got some little plugs that I can plug in, and I can put the electrical energy back in, and I can essentially reverse those reactions. I can make the electrical energy be converted back into chemical energy. I can drive a chemical reaction, and then the next day I can go out and about and use my fancy little power bank there. So electrolysis, we're using electricity to drive a chemical reaction. There's a conversion there. We have a substance being broke down called the electrolyte. So this is an example of electrolytic conductivity. The flow of ions in an ionic fluid causes a chemical change. So electricity, electrical energy, we can think of as the flow of charge. Predominantly, we think of this as the flow of electrons, but our ions as charged species can also carry a current by moving because they are charged. Positive cations, negative anions. Importantly, with all this, is that the charged particles need to be able to flow. They need to be able to move because that's how they conduct the current, by moving. So in our electrolytic conductivity, our ionics need to be fluid. They need to be liquid or aqueous. I mean, they could be gaseous, but that would be quite difficult to do. So we're going to look at electrolytic conductivity occurring in aqueous and molten ionic species. So electrolysis occurs in electrolytic cells, where we have something called an anode, where anions can move towards the anode and they can undergo oxidation. They can lose electrons, and they will have a cathode, where cations will move to the cathode and they can be reduced from the electrons that were lost at the anode. The cations can gain these electrons at the cathode. Electrostatic force of attraction, opposite charges attract. So in an electrolytic cell, if anions are moving towards the anode, Therefore, it's got to have the opposite charge. Anions are negatively charged, so our anode in an electrolytic cell is positively charged. Cations are positively charged, so if they move into the cathode, that means it is negatively charged. What does this look like? It looks a little something like this. This is typically how these electrolytic cells will be drawn. There's a few different kinds of specific electrolytic cells, but they're all going to have key features that are identical in every instance. These key features include two electrodes. We have the anode and we have the cathode, two electrodes, opposite charges. Our electrolyte, this is our ionic fluid. We said here the substance that's being broken down is the electrolyte. It has to be an ionic fluid. So that means that we have positive cations and we have negative anions able to move. Might be molten, might be aqueous in the electrolyte here. So we have anions that move towards the anode. In fact, I might color code this a little bit nicer. So let's say we got our blue positive cations. We'll have our pink negative anions. So anions are going to move towards the anode. And the reason they move towards the anode is because it's going to end up with a positive charge. At the anode, the anions undergo oxidation. They're oxidized. So they're going to lose electrons. So our anions undergo a half reaction here where the electrons will be lost and the electrons are then able to flow throughout the circuit, which is what I've shown here. I've shown my flow of electrons. They're going to move towards the other electrode, which is the cathode. And the cathode, this here, is where the cations are going to be reduced. So then the cations are going to move towards the cathode. And this is where the reduction is going to occur. They're going to gain these electrons that the anions over here had lost. Cations with a positively charged, they're going to move towards the negatively charged cathode. Now, all of this can be brilliantly summarized in a fancy, I mean, it's not fancy, I don't know why I said fancy, in an acronym where you can imagine an oil rig cat. Imagine a little cat hanging out on an oil rig, as I'm sure they would like to do. I mean, all of electrolysis can nearly be summarized in this. You have an anode, if I go back to my color coding, so you have an anode. At the anode, oxidation occurs, where oxidation is the loss of electrons. Conversely, you have the other half of it, if we can think of it like that, where you have a cathode. At the cathode, we have reduction occurring, which is the gain of electrons. The anode, oxidation is lost, reduction is gain, occurs at the cathode. It can all be summarized as an oil rig cat. What else do I have on here? Importantly, we have the whole reason this reaction is occurring is because we're using electricity to make it occur. So we need to include a power supply, which will be a direct current. So that's what I've shown up here. That's how you draw your power supply, all those little physicsy circuit diagrams. The longer line on the positive side, the smaller line on the negative side. You can remember that by, if you got the longer one, you've got to snap it in half to make a positive sign, whereas the smaller one, just the negative sign, if that helps you remember. Brilliant. So using electricity, our power supply to drive this chemical reaction, because without the electricity there, our electrolyte is just going to remain down here unchanged. Another little acronym that we can apply for electrolytic cells is panic. If you ever forget what electrode is charged which way, you've just got to panic, where it's saying the positive is the anode and the negative is the cathode in an electrolytic cell. Really important that this only applies for an electrolytic cell. We're going to look at other kinds of cells, but in an electrolytic cells undergoing electrolysis, the positive is always the anode, the negative is always the cathode for electrolysis. An oil rig cat is always true. Oxidation always occurs at the anode, reduction always occurs at the cathode, but we're going to see other types of cells where the charge on the anode and the cathode isn't necessarily what we see here. So we can then incorporate our half reactions. We know that we have an oil, we have oxidation at the anode, so we can show the oxidation reaction occurring at the anode. So I've just got X for some sort of anion forming X, usually a molecule if we're dealing with our nonmetals and we're losing the electrons. These electrons being lost are the ones that are going through the circuit, and the electricity is allowing these electrons to be lost so that the cation can gain the electron and form whatever the product is there. So you can see here we're having chemical change different to our metallic conductivity, where the electrons pass through a metal unchanged. In this instance, we're chemically altering what our ionic species was before. Let's get into some examples of electrolysis. As we said earlier, it needs to be an ionic fluid. So we have two options. The first of which is the electrolysis of molten compounds. Molten ionic compounds can conduct a charge because they're in the liquid state. Therefore, these ions are free to move. These are a bit more straightforward in order to predict the products, because there's only one type of cation, there's only one type of anion, so there's only one thing that can be oxidized, there's only one thing that can be reduced. For example, if we had the electrolysis of molten magnesium fluoride, that means that we would have liquid magnesium ions in there, and we would have liquid fluoride ions in there. So at the cathode, the cation can be reduced to the metal. At the anode, the anion can be oxidized to the diatomic molecule. So the kinds of questions that we get with electrolysis would be to draw electrolytic cells, which we'll do in just a moment. It will be to predict the products, write half equations, write overall equations, and then to also predict observations. So what would you see if you had this electrolysis unfolding before you? So for example, in the case over here, we would see the production of a silver solid. We would see magnesium metal being produced, which will be that silver solid. At the anode, we would see bubbling of fluorine gas if we're making molecular gases. If these molecular gases have particular colors, like our halogens are known to have, then we can be even more specific and say what color gas is being produced at the anode. Let's give it a go now. Draw an electrolytic cell for the electrolysis of lead bromide. Show the products that will form, write an overall equation to represent this process, and state what would be observed. So putting it all together, drawing your electrolytic cell. Science, we always have nice, large, ruled diagrams. So there you go, I've given you the template there. See if you can pop all of this information onto that diagram. Pause, and then we'll have a go together here now. So really important to practice drawing these electrolytic cells. You're going to be drawing them quite a bit, and there's lots of detail you want to include on them. So you want to make them nice and large so you're not squishing it all together, and you want it ruled and neat. So what do you draw? You draw your container, your vessel, which is what I've got there. You draw your two electrodes, which is what I'm trying to draw here. Oh, there we go. And then you're gonna have your electrolyte. So importantly, our electrodes need to be submerged into the electrolyte. I mean, that might be a bit obvious. The reaction can't take place if the electrodes aren't in the electrolyte. And then you've got to complete the circuit. So you're going to have your power supply like that. So there you go, that's the template for these electrolytic cells. And then I like to just pop a little bit of information on there. So we've got the positive side, the larger one there. So we can say this is going to be our positive anode. And we're gonna have the negative cathode. I'm drawing the anode on the left and the cathode on the right. Doesn't really matter unless you're told otherwise which way to draw it, as long as everything's consistent, as long as you've got your electron flow in the correct direction. Because obviously this is a two-dimensional representation of a three-dimensional object. So that's our electrolytic cell. Let's start to put some more information. So we were doing the electrolysis of molten lead bromide. Lead bromide in the liquid phase. So in here, we're going to have lead cations. I like to draw a few in there. And we're going to have the bromide anions. Should we get a little bit of color here? Don't have to make it color coded, but color is always good to make it a little bit clearer. Bromide anions there. What's going to occur? Our bromide anions are going to be attracted, electrostatically attracted to the positively charged anode. Anions move to the anode in electrolysis. So we can represent that with some arrows there. What is occurring here is they are losing electrons. They undergo oxidation at the anode. An oil rig cap. Paint it on the inside of your eyelids. Very, very important little acronym. So if we got oxidation occurring at the anode, let's show this half equation. We have bromide ions that are going to be liquid, and bromide ions, when they form the element, is going to make a diatomic molecular gas plus an electron. We got to make sure it's all balanced. We've got two bromines in the diatomic molecule, so two bromides. So two bromides have to come together, and they're going to have to lose 2 electrons to make that half equation at the anode, oxidation at the anode. Then what is occurring? We have our electrons lost here. These electrons are going to move through the cell. So you want to show the movement of electrons, which you can do with an arrow and label it. So I'm saying the electrons are moving from the anode, where they're lost, to the cathode. At the cathode, we're going to have our cations be electrostatically attracted to the negatively charged cathode. And at the cathode, we have reduction occurring. So they're going to gain these electrons, which we can show in our reduction half equation. So in this instance, we have our lead, our Pb2+ liquid, and we're gaining 2 electrons to form lead solid. All right, how much of the question have we done? Because it was a multifaceted question. We've drawn the electrolytic cell. We've showed the products that will form. We've got to write an overall equation to represent this process and state what would be observed. So what are we going to have for the overall equation? Overall redox equation is going to look like this. We have 2 electrons being lost at the anode. We have 2 electrons being gained at the cathode. So this is already balanced in terms of electrons being lost and electrons being gained. Recall that the electrons being lost need to equal the electrons being gained. So if it was uneven, then we would have to multiply and make sure they were even. But in this instance, we can just put them all together. So we're going to have our 2 bromide ions and our lead ions. It's molten, so they're both in the liquid phase. I'm going to run out of room, aren't I? I reckon I can squeeze it in. And we're going to form lead metal and bromine gas like that. Brilliant. So just the left and the right hand side of the arrows, combining them together there. Another way you could write this is we could just write that we have the lead bromide that we had. So we had the PbBr2 in the aqueous. So instead of writing it as an ionic equation, just doing it like that, both showing the same thing. Fabulous. So there's our overall equation that we have. The final thing is asking for the observations. What would we see in this electrolysis? Well, what are we forming? We're forming lead, which is going to be a silver metal. So at the cathode, we would observe, a coating of silver solid over the cathode as those lead ions are reduced to the lead atoms. And then at the anode, we're forming bromine gas. So we would observe bubbling. We would observe a gas being given off. And we know that bromine has that brilliant reddish color, doesn't it? So we would observe at the anode, we would observe a red gas being effervesced. Fabulous. So that's what we put all together. Oxidation half reaction, reduction half reaction. Flow of electrons, a really easy one just to forget. Always include your flow of electrons in your electrolytic cells. An overall equation down there, molten lead bromide forms lead and bromine gas. Recall that electrons lost from oxidation need to equal electrons gained from reduction, which in this instance they very much do. Really important though, this reaction doesn't occur if we're not supplying that electrical energy. That's what electrolysis is doing, converting electrical energy into chemical energy. So there are our molten compounds. We can also have electrolysis of aqueous compounds. Now these get, one extra step complicated because we'll have our ionic cations and anions. So, let's say if we got some sort of ionic solid where we got the metal and the non-metal in an ionic, that's going to dissolve, that's going to dissolute to form the cation and the anion. But what we also have is we have water. Oh, I wrote fluorine again. X, I'm just representing X as, whatever our anion is there. But we also have water. So our water can partially dissociate into hydrogen ions and hydroxide ions. So we've now got an instance where we've got two species that can potentially be reduced, and we've got two species that can potentially be oxidized. So the question becomes, which one do we reduce and which one do we oxidize? Lucky for us, there are rules that we can use. Rules based on selective discharge, selecting which one is going to be discharged. Aqueous solutions, similarly, ions free to conduct a charge if they're able to dissolve into water and free to move into solution. But like we said, we've also got our hydrogen ions and our hydroxide ions. So competing ions, we need to determine what's going to be reduced and what's going to be oxidized. Will it be the H plus or will it be the metal cation? Where we've talked about reductions of metal cations, but if it's the hydrogen ion that's reduced, hydrogen being a non-metal is going to gain electrons, but it's going to gain electrons to make diatomic hydrogen gas, a diatomic hydrogen molecule. Or will we have oxidation of the hydroxide as opposed to oxidation of our anion that we've been looking at? So if we have oxidation of hydroxide, a bit more complicated because it's a polyatomic ion, but this is what the oxidation of hydroxide will form, 2H2O plus O2 plus 4E minus. So we have the loss of electrons and we would observe oxygen gas being effervesced. So there's rules. In the case of our cations versus our hydrogen ion, which cation will be reduced, it's determined by the reactivity series. If the metal is more reactive than hydrogen, then hydrogen gas will be produced. But if the metal is less reactive than hydrogen, then the metal will be produced. So we have to consult the reactivity series. I've just gone and Googled one here. So, reactivity series, this is a simplified one, doesn't have everything in it, but we've got our metals, and then we've got our non-metals there, carbon, but importantly for us, hydrogen. So if the metal is above hydrogen in that reactivity series, it means it's obviously more reactive than hydrogen. So let's take a really extreme example where we had potassium. Potassium metal, super reactive. That potassium ion does not want to go back into the potassium metal if it doesn't have to. It would much rather be the potassium ion. Being more reactive, that potassium ion is much more favorable to remain that compared to the hydrogen ion. So potassium being so much more reactive than hydrogen, if there's the choice, quote unquote choice, I have a habit of personifying, subatomic, well not subatomic, but atomic particles that obviously don't have free will and wants, neither here nor there. But it's a helpful way to consider it. This potassium being so much more reactive, the hydrogen is going to be reduced. It's going to be selected to be reduced over the potassium is. Conversely, if we got hydrogen here, if we have a metal below hydrogen, we have the same idea, but only this time the hydrogen is more reactive. So, if we had a copper species where we've got copper in solution, the hydrogen ion is going to remain ionized over the copper because it's much more reactive. It would be more difficult to revert the hydrogen ion back to hydrogen gas compared to the copper. So all that to say that if we have a metal more reactive than hydrogen, hydrogen gas produced. If the metal is less reactive than hydrogen, the metal will be produced. For our anions, we have rules as well, which anion is going to be oxidized. It's also determined, by how easily discharged it is. Simple ions such as chloride, bromide, iodide, and our hydroxide are easier to discharge. So in this instance, it becomes a matter of concentration playing effect. So an anion in higher concentration is always preferentially discharged. Suppose you could just think of that as being a more statistic likelihood. If we got lots and lots of chloride compared to our hydroxide, it's more likely that the chloride is going to find its way and be oxidized at the anode. Because this hydroxide, this dissociation, there's a really, really, really small amount of hydroxide. So if you have a very concentrated chloride, bromide, iodide solution, then the higher concentration is going to be preferentially discharged. Now, if we have more complex ions, such as our sulfate, nitrates, carbonates, these are much harder to discharge compared to our simple ones. So in general, will not be discharged. The hydroxide will undergo oxidation instead. So if you see sulfate, nitrate, carbonate, ionic electrolyte, then we're going to have the oxidation of the hydroxide. If we have a high concentration of a simpler ion, such as the chloride, bromide, or iodide, then we'll have the oxidation of the simple ion. Let's put it all together. Let's do some electrolysis of aqueous compounds. We can now use our rules for selective discharge to determine what's going to be oxidized and what's going to be reduced. Again, we can predict both observations and the products. And unlike the molten compound, we're going to have something that remains behind in the electrolyte. Now, this could actually end up being something different than what we started with. Let's have a look. Let's do an example and it will all come into fruition. In these kinds of aqueous compounds, you're going to see some other kinds of electrolytic cells, especially if you're making gases and you want to keep these gases, such as a Hofmann voltmeter. You can give that a Google if you want. That's one you're likely to come in contact with when you're doing these kinds of questions. But importantly, the key features are always the same. It doesn't matter what the electrolytic cell looks like. You're always going to have an anode. You're always going to have a cathode. You're always going to have a power supply. You're always going to have an electrolyte. It just might be arranged in a slightly different configuration. All right, here we go. We'll get to the question. For the following electrolysis reactions, draw a fully labeled electrolytic cell, predict the products that form, and what will be observed. So we have concentrated sodium chloride and dilute sulfuric acid. Pause, do all that, and we'll check it now. I'm going to cheat a little bit here because I've already got a diagram I can use, but you've drawn out your nice labeled electrolytic cell showing the cathode, the anode, the electrolyte with your power supply. Now we can start to work out some products. So in concentrated sodium chloride, what do we have? We've got, this is how I like to set it out and consider it. We've got sodium ions and hydrogen ions. And then we're also going to have chloride anions and hydroxide anions. So let's start at the anode. Let's determine what's going to be oxidized. Will it be the chloride or will it be the hydroxide? Well, we've got a simple ion and we have lots of it. It's concentrated. So our selective discharge rule tells us that the chloride ion will be the one that is oxidized over the hydroxide. So our chloride will turn into chlorine gas at the anode. So what we would observe is some bubbling of yellow-green chlorine gas. We know the color of that chlorine gas, yellow-greeny. We would see that be effervesced, the yellow-green gas bubbled off, which you certainly would want to keep your distance from. We have the oxidation reaction occurring here. So our electrons will be lost, and we can represent that with a half equation. So the chloride anions are going to lose electrons to form diatomic chlorine gas like so. We're going to make that nice and balanced. So we need two of them and we'll need two of them. So there you go. There's our half equation showing the formation of the chlorine gas. The electrons are lost here. They're going to flow through the circuit. Always show your electron flow with some arrows going from the anode to the cathode where the reduction will occur. Now, the reduction, we've got to determine what will be reduced. Will it be the sodium or the hydrogen? Well, our sodium is so much more reactive than the hydrogen. So the sodium is not going to be reduced back to that really reactive metal. Instead, the hydrogen, much less reactive, is going to be what is formed. So we'll form the hydrogen gas. So the hydrogen ions will be converted to hydrogen gas. So at the cathode, we would also see bubbling, but it would be a colorless gas because hydrogen doesn't have any color. And this is where the reduction reaction is occurring, which we could write as our H+, aqueous, is going to gain electrons to form diatomic hydrogen. I don't need two of them, just one of them, diatomic hydrogen, and we got to make sure that's balanced. So two of them and two of them. This is why you want to make your diagrams nice and big, lots of information to include on them. Now, importantly, there's actually a third product. So we've said what's going to be observed. We've predicted the products at the anode and the cathode. We're forming chlorine gas, we're forming hydrogen gas. But if you look down here, what's left behind in our electrolyte is sodium ions and hydroxide ions. So the electrolyte's also going to be converted into an aqueous solution of sodium hydroxide, because that is what will be remaining in the electrolyte once the chloride ions have all converted and the hydrogen ions have all converted. So when it comes to predicting the products, we would see a colorless gas at the cathode, which is the hydrogen gas, yellow gas at the anode, which is the chlorine gas, and then the sodium hydroxide solution will be what remains. What about down here for our dilute sulfuric acid? This is an interesting one. In this instance, we have hydrogen ions from the sulfuric acid, and we also have hydrogen ions from the water. So I mean, in this instance, the hydrogen has to produce, there's no other options. But we have sulfate anions, and then we have hydroxide ions from the water. Sulfate from the sulfuric acid, hydroxide from the water. Let's color code this again to make it a bit more clear. So let's go through the process once again. The anode, which anion is going to be selected? Well, we said complex ions are never discharged. So the sulfate won't be discharged. Instead, it will be the hydroxide that moves to the anode, and we will get the formation of our oxygen gas. So we'll get our oxygen gas being bubbled off, which we could represent, I'm going to run out of room here, which we can represent with our equation. We said that hydroxide, if it's aqueous, if it's being oxidized, we form some more water, which is just going to remain in the solution there. But importantly, we get those oxygen molecules being formed, which is what we'll observe, the colorless gas bubbling, and then the electrons that can move through the circuit, show your electron flow to the cathode where the reduction will occur. And we've said, well, hydrogen is all that is there. So the hydrogen is going to be reduced to the hydrogen gas. So we'll get the same equation that we had before. 2H plus aqueous plus 2E minus goes to hydrogen gas, like so. Yeah, nice one. So we would get colorless gas bubbling at both electrodes, where we'll end up with a 1:2 ratio. The colorless gas both at the anode and the cathode, that is a 1:2 ratio of oxygen to hydrogen. Why is that? Well, let's put together our half equations. So let's say at the reduction, we said that we had 2H plus aqueous plus 2E minus go into H2 gas. And then our oxidation reaction, we had 4OH minus go into 2H2O plus, that's liquid, plus O2 gas plus 4E minus. And then I'll get a nice straight line, not a highlighter, straight line, there we go. So we're gonna make the electrons equal each other. So this first one, we're gonna have to multiply by 2 to get 4H plus. I've still got my straight line tool. To get 4H plus, 4E minus, and then 2H2. So let's put it all together. We can cancel out the 4E minus there and the 4E minus there. And what we end up with is we end up with 4H plus 4OH minus. So let's put that together and just say 4H2O goes to 2H2O plus O2. Well, we've got the same thing on both sides of the equation. So, you know, 2 of these waters are remaining unchanged. I forgot the 2H2 as well. So down here, we've got 2H2O liquid goes to O2 gas plus H2 to H2 gas. So if you recall, this was the electrolysis of dilute sulfuric acid. But essentially what we're doing is we're just converting water into oxygen gas and hydrogen gas. So electrolysis of aqueous compounds taking into account both the cations that are present and both the anions that are present. And that concludes our overview of electrolysis. We predicted the identities of substances liberated during electrolysis from the state of electrolyte, you know, molten or aqueous, position in the redox series, and concentration. Tasks: if you would like to consolidate your understanding of the concepts covered, pause, work through each column one at a time. Thanks for your time. I look forward to diving into electrolysis in a little bit more detail with you in the next video. Enjoy your afternoon. See you later.